Hello and welcome to this tutorial, which is addressing the issue of the brace forces during deck placement of a curved tub girder bridge. This is actually an important issue for curved tub girders, as the brace members are primary structural elements, and the design forces, in other terms, the maximum forces they will ever see is actually during the placement of the wet concrete. So if we go here to this features form, we can see we have a curved bridge, stiffeners, diaphragms, cross frames, lateral trusses. These are the members we are most interested in here. We've got struts. We are actually checking this box erection analysis. It means that we're not explicitly modeling the deck. We are instead modeling the weight of the wet concrete using a uniform load here. We've also got splices or transitions and pin and roller supports. So I won't go too much in detail here. You've seen it before. The radius of curvature is equal to 700 feet. The curvature has a left orientation. This is the length of the tub. These are the material properties for the steel. I have 4 supports here. I don't need to have any pin because of the curvature of the bridge. So this is stable in itself. I don't need to have a 1 anywhere. 0 means pin, it means a roller, sorry, and 1 would mean a pin. Okay, this is all here again. This is where I define the splices or transitions. I've got 51 stiffeners along the tub. 3 means that there's a stiffener on both the left and right web. I've got 4 interior diaphragms at the ends and at the third points. I've also got 24 interior cross frames, which are uniformly spaced at 20 feet along the bridge. I've got 54 lateral trusses, which are really top lateral braces, and you can see here they have this orientation 2, 1, 2, 1. So 2 and 1 means whether the brace goes from the right to the left top flange or instead to the left, from the left to the right top flange. So here it is following kind of a stitching pattern. It will do something like this, 2, 1, 2, 1. Okay, we will see that visually as we complete this modeling process. We've got also 27 struts, which are just axial members, which are orthogonal to the tub, and because of their direction, they do not provide any stiffness against the cross-sectional distortion. So they are not very effective in preventing the twisting of the section, as we've seen in a previous tutorial on the Marseille Bridge, which tragically collapsed about 20 years ago. We don't need to click on this button again because we have already modeled this bridge and we haven't touched the reference points. So we can just click on next. We have a pretty coarse mesh, but that's because the bridge is pretty long, and we should not also forget that the shells in Embrace 3D are quadratic shells, so we actually have a node every 24 inches, every 2 feet. These are the cross-sectional profiles. Okay, this is a constant web depth. Here we are assigning the right profiles to the different segments. We have clicked on the default button because we are in this situation where we have a constant web depth, so we don't need to worry about this. The program will automatically fill this out for us. We are turning on the full length of the bridge. We are turning on the cross frames. We are defining a uniform load which captures both the self-weight of the bridge and the weight of the wet concrete. This is why we don't need to turn on the self-weight here. This will already be captured in the load here, the uniform load. We can hit this button. We've, however, already run the model, so instead we can just go to Viewer here, extend this, change the view, and as you can see, we have the uniform load here acting on both top flanges. We can also check and let's turn off the loads here. We can check the cross-sectional profiles. This is something I strongly recommend to check the assignments. Okay, we can go to a top view and see how the bridge looks like. It looks okay. Let's maybe zoom in again to check the bracing. You can see these would be either struts or full cross frames, and in between we have the top lateral bracing. Okay, let's go back to this isometric view, and now let's actually shift the model a little bit. To go faster, you may click on that button more slowly, like here, and let's visualize the displacements. The maximum displacement is equal to about 6.3 inch at midspan. Of course, we can look at the sigma YY stress. Let's look at the stresses on the top face. We can see we have a maximum tension of about 23 KSI and a maximum compression of about also 23 KSI. We can look at the cross frames either visually here, but it's kind of hard to read. Okay, we may want to zoom in, etc., but it's kind of hard to read. So instead, we can just go here and go to charts, brace forces. And this will really tell you in just one chart where are the maximum and minimum forces on the cross frames. So here, as we said, we're interested in the lateral truss forces, the top lateral bracing. So we will just enter zeros here and hit refresh. And you see the maximum compressive force that the lateral brace will see during the placement of the wet concrete. That force is equal to about 38 kips. So that's a pretty sizable force. It's not a huge force, but this will be the design force, okay, for that member. And in tension, that force is actually slightly higher. It's about 45 kips, okay. Of course, the pattern is symmetrical because the bridge is symmetrical. Now, if we want to check, say, the forces in the cross frame diagonals, we may enter ones here and zeros up here and then hit refresh, and we would see that these cross frame forces are slightly lower. Okay, they're equal to about 11 kips in tension and minus 10 kips in compression. So I hope this tutorial was useful. It is again one of these nice tutorials where you can see the benefits of having a full 3D shell model instead of a line model, instead of a spine model, which would be enabled to capture both the bending along the primary axis and the cross-sectional distortion here due to the torsion which is inherent to the curvature on that bridge. Okay, so I hope you have enjoyed this tutorial, and please stay tuned for further tutorials on plate girders and top girders. Thank you.